Okay, so today's speaker is Kuehn from Technical University of Munich, who will be talking to us about stochastic waves, I think something about translating and rotating. Why don't you let us know all about that?
Okay, thanks for the invitation. It's a pleasure to give this talk, although I have to say it's now 11 in the evening here, so which is, I think, now 2 in the afternoon Vancouver time. So if I'm slightly sort of looking tired, it might be because I am. So let me go for it anyhow and see what I can convey about stochastic waves. So what's this topic about? So that's the plan for today. I will give you a little bit of background and motivation why you should look at stochastic waves and not only deterministic waves, and give you a bit of background on stochastic partial differential equations, SPDEs, which I think is an important tool. I mean, in biology, many things are spatial and they are stochastic. So, and they're differential equations. So a little bit of knowledge about SPDEs can't hurt. Then I will go over traveling waves. So basically stuff that sort of gets translated, as was alluded to in the introduction. And I will present a few results about the Nagumo equation and the Fitzhugh-Nagumo equation in one spatial dimension. And then I will actually go to the most recent stuff in the very end, which is about spiral waves or rotating waves, where it's about, you know, patterns that are actually happening for a 2-component system in 2 spatial dimensions. And I will tell you a little bit about the mathematical results that we have obtained with a number of colleagues over the last few years. All right, so let's get started. So what's the motivation? So the examples and the equations I'm mostly looking at are partial differential equations, and I will put them on a domain. Could be RD, could be a bounded domain, but in most cases it will be some variant of RD with d equal to 1 or 2. The unknown I will denote by u of x and t, and eventually I will also force these equations by a space-time stochastic process psi of x and t. I will specify that process on the next few slides, but you can think of that's just a noise process that is sort of noisy and depends upon space x and time t. And some of the sort of models that I will look at and that motivated me to look at this are sort of very classical reaction-diffusion equations. So the first one here is the FKPP equation, the Fischer-Kolmogorov-Petrovsky-Piskunov equation, which is sort of a quadratic nonlinearity with normal sort of diffusion term here, and then a noise term that I will specify when time comes. And then the second equation that motivated me a lot is this, also very classical in math biology. Most of you will know this is the Nagumo equation, which in other areas is called the Allen-Kahn equation, or the real Ginzburg-Landau equation, or the 5,4D model, or the model with an Elie effect, or the Schlögel model. All of these things are effectively the same type of equation. It's a sort of cubic polynomial nonlinearity with the normal sort of semi-linear heat equation type. And then usually I will look at additive noise in this case. And then sort of in, more sort of realistic model, still a model, but still a bit more realistic, is the Fitzhugh-Nagumo equation, which is also used a lot in mathematical biology, neuroscience particularly, but also in cardiac dynamics a lot. Which is sort of the Nagumo equation sort of coupled to another variable in neuroscience that would be the gating variable for a neuron, and U would be the, the voltage. And then also this equation you can study with noise, and, so these are sort of classical reaction diffusion models, and I would be interested in the dynamics of how these sort of equations behave actually under the influence of noise. So deterministically, of course, many of these things are quite well understood. Yeah, very good. So that's a good motivation for the equations that we are going to look at. And so let me do a little bit of mathematical background, because I don't expect that all of you are really experts in stochastic partial differential equations. But I will slowly go through this and at least explain you a little bit what you might need to know to really study these, spatial stochastic models. So my base construction for the noise will use a Hilbert space. You can think of this, for example, L2 over your spatial domain. Yeah? And then you take an operator Q on this Hilbert space, which is linear, symmetric, non-negative. And then I will use its eigen decomposition. So I will, assume that it has eigenvalues rho k and eigenfunctions qk that are orthogonal in this inner product, in this Hilbert space inner product. And then I will take an infinite chain of IID Brownian motions, and then I will define a Q-Wiener process W, or W of the space variable and the time variable, just as this series. This series basically has two parts. One part that comes from the spatial component, which are these eigenfunctions qk and these eigenvalues rho k. And then there's the sort of time part, which are the Brownian motions beta k. And that series, under reasonable assumptions, can be shown to converge. And I will denote the time derivative of W as psi. This is my noise process that was my forcing. And in general, I have to already sort of tell you that this guy is, of course, as you know from normal Brownian motion, pretty ugly. If you have a normal Brownian motion, you differentiate in time, then you only get a generalized stochastic process. So this psi, mathematically speaking, is only a distribution, so a generalized function. But, you can still define it as a generalized function, and that's perfectly reasonable. So convergence of W under reasonable assumptions, like, for example, trace class, but even if it's not trace class, in some cases also the identity, if you do sort of an embedding trick, then this W converges, and it's a very nice stochastic process with values that has continuous path. So these are continuous path in time with values in your Hilbert space, because you have an evolution equation that actually lives on that Hilbert space. So what's the interpretation of this funny Q if you compute? And if you compute actually the sort of correlation function of your noise, so of the time derivative, then you see that indeed you can sort of interpret that this Q becomes in the end like a kernel. So you could specify Q via a kernel, little q. So this operator could be an operator just specified via that kernel. And then you can interpret basically Q as the spatial covariance. Lots of steps I'm skipping here, but roughly speaking, you should think that via specifying Q, you specify the spatial correlations of your noise. That's really what you are doing. And then there's a mathematical remark. So the regularity is usually pretty ugly. So as I say, this psi, which is the time derivative of W, is usually only a distribution, a generalized function, and it only has negative regularity in some funny Hölder space. So it's pretty bad. So this is one of the problems of this whole business, that somehow the forcing you are basically applying to your equation, which you can think of as a time, space, and time dependent forcing, is a pretty ugly guy. Yeah. So, and that gives you lots of technical complications. All right. So what are solution concepts for these SPDEs? Let's suppose we think of these types of equations. You can write them on the left-hand side in a mathematical formulation. So a little bit like the classical Ito type or Stratonovich type formulation. I will use Ito formulation. Or you could write them in the physicist notation that I used on my sort of motivation slide, where it's basically just a reaction-diffusion equation plus a forcing. So there are many different solution concepts. One would be strong solutions, but strong solutions are usually not very nice, because normally this process U here, this doesn't have enough derivatives to justify sort of taking all the sort of derivatives in the solution. So strong solutions are not so good, but mild solutions are good. For the mild solution, you take the semigroup associated with the Laplacian, you convolve the nonlinear term with this guy, with this semigroup, and you do the same type of convolution also here. And then this indeed gives you, this should be, I'm sorry, this should be a DWS. So there's a typo here, very sorry, this D has to be moved up front. It's a DWS, so a stochastic convolution. And you could also define weak solutions. So you test it in a suitable inner product. And then for all test functions in the domain of your operator, you can actually sort of specify that that's a solution. And there's also a recent concept that, won Martin Heira the Fields Medal in 2014, which are renormalized solutions, where you sort of massage the equation a little bit and renormalize it with some terms. I will not use these today, but I will mostly focus on mild solutions and weak solutions, which are concepts that you're very well aware of from classical PDE theory. And basically, you can lift those to SPDE theory. So that's the solution concept I will use. So now let's look a little bit at the dynamics, because that's what we are really interested in. We are interested in how these equations behave. I mean, solution theory is all good and fine, but from a biological viewpoint, at least, we should look at the actual dynamics of these equations. And as you all well know, one of the main sort of things that are important for the deterministic case when sigma is equal to 0 for these sort of scalar or simple reaction diffusion equations in the scalar case when there's an unbounded domain are waves. Yeah, so traveling waves. So what is a wave? Well, I'm preaching to the choir, I guess, here. So a wave is just a solution U that has a profile in X and that gets translated at a fixed speed C in time. And for the Fisher-KPP equation and for the Nagumo equation, this is relatively well studied. It's very well understood in the deterministic case for sigma equal to 0, what these waves are when you're in the scalar setting of the real line. You know that they are basic propagating fronts. So they are wave solutions that connect between the two stationary states for Fisher and for Nagumo, which are two of them are located at 0 and 1. And you can show that they're indeed fronts, which means that there's a profile, and this profile as the traveling wave variable eta, which I define as x minus ct tends to plus and minus infinity, this goes to the relative end states of the front. So it goes on one side to 1, on the other side to 0. So these are classical traveling wave solutions that just get shifted in time by these deterministic equations. And I guess most math biology courses and textbooks and so on have this, so let me not dwell on this too much. Let me rather raise the question, now if I add noise to this equation, which comes, for example, from microscopic disturbances, external forcing, the micro to macro limit of finite particle systems, there's many sources where this noise term could come from. What would be the definition or the construction of a stochastic wave? So how would I actually think about a stochastic traveling wave? Which is very reasonable. I should think of these objects. So here's some sort of very upper level, sort of high level introduction to this. So here I've taken the Nagumo equation and I have sort of fixed my noise to be multiplicative. And I've assumed that at the ends of my wave, I've clamped the wave down so that there's no noise basically at plus and minus infinity, which is perfectly reasonable. You can show that these solutions actually stay between 0 and 1 if you start between 0 and 1, if you assume that the noise term, remember, this is the noise term here, that this noise term vanishes at the end state. And then I just let the equation run with a sort of nice trace class, so Q trace class operator noise. And then I see that in time, so these are different time snapshots of the solution, that in time, the solution just moves like a traveling wave, just that it has these additional wiggles, basically, which is sort of expected. And then the question is, sort of, I need to track the solution by a certain marker, because I don't have a fixed wave speed anymore, because the wave speed somehow becomes stochastic. So somehow I need to define, and this M is just an example on the right, I need to define some marker, some basic observable that tells me where my wave currently is. In the deterministic setting, it's pretty easy because this marker would be just the wave speed times t, because you have a sort of fixed profile that gets translated at a fixed speed. But for a stochastic case, a priori, there is no fixed speed. So I need to somehow recenter my wave with a time-dependent observable to make sure that I can actually understand this. And there's here a little bit of a plot of one marker that I will show you on the next few slides that somehow tracks where the position of the wave is. Then this sort of wiggly line tells you the actual computed position for one particular wave of this marker. And the dashed line tells you a sort of sampling over quite a number of waves. So it's like the mean value of that M. And the sort of dotted guys tell you the variance, sort of one standard deviation around the mean. So roughly speaking, you can sort of track then the marker, which would be the position of the wave. And then you could say, instead of deterministically trying to analyze solutions that are x minus ct, you could analyze solutions that are x minus some marker quantity of t. And the sort of basic principle of this stochastic traveling wave business is, in the end, the wave speed c is not fixed, but you will obtain the dynamics for this marker itself. So there will be a low-dimensional, in this case, one-dimensional stochastic ordinary differential equation that tells you how this marker is evolving. So how this sort of, wiggly path here on the right is evolving. And this is basically like, the phase or sort of the actual evolution of the phase of that wave. And it gives you a little bit of an idea how you are sort of wiggling around the deterministic wave speed if the noise is sufficiently small. And then this is basically giving you the fluctuations of that wave, this SODE, along the translating direction that deterministically sort of you are used to. So you're basically getting the normal speed plus sort of a fluctuation, which is sort of like a phase diffusion around this sort of classical deterministic speed. And then you prove that there's another direction, a direction that's actually sort of perpendicular in a suitable function space to the time derivative, to the derivative of the wave profile with respect to the traveling wave variable, which is basically the, the direction along the wave, the translating direction, the sort of symmetry that comes with the translating symmetry of the waves, sort of transversal to that or orthogonal to that. There is a direction which is an infinite dimensional system that captures the fluctuations that are happening sort of away from the translating direction. That's the sort of big level picture of how you track these waves. Okay. And I've written a little bit of a review, which is in this Jahresberichte der Deutschen Mathematikervereinigung, where I explain this a little bit and I give you a couple hundred references of what people have tried. Okay. So now let's look at how to define this funny marker quantity, because you could take many choices now in the stochastic setting. In the deterministic setting, it's C times T, but what do you do otherwise? You could define, for example, and say the position of that wave at time t is simply given by looking at level sets. So you're basically looking at your solution, you're checking when it reaches a certain level set, and by that, you are actually tracking the actual m of alpha t. So that's basically one way to do it. Yeah, so it's basically that when you hit a certain level set, yeah, at a certain time. You could take an average, you could just say on a finite domain, which is sufficiently big enough, I check the area under my curve. And of course, the area under my curve is moving. So it would tell me where my wave is relative to this sort of area that I have computed. Yeah. And this is actually the stuff that I plotted here on the upper right. It's just over a fixed window, the area. And of course, that area is changing if my wave is moving. And it's sort of more robust than just the speed, because somehow it just tells you sort of an average quantity. But the area is not so nice for mathematical purposes. For mathematical purposes, what you're actually doing is it's much better to compute this marker as a sort of solution of an optimization problem. What is the optimization problem? I'm looking at the marker, which is actually telling me how far away am I from a certain reference profile. The idea is I take my deterministic wave, for example, as a reference profile. So uref would be my deterministic wave, optimize this, say, in L2 over the real line. And I say, okay, the minimum value y is actually sort of the best possible translate of my deterministic wave profile that the current stochastic wave profile is currently close to. So you're basically minimizing the distance between the deterministic wave that you know and the stochastic wave that is traveling. And if you look at this minimization problem, then you actually can show that a necessary condition for minimization after you do all the derivative is, for example, that this is satisfied. So you can get out of the usual just differentiating, you get that indeed that there are certain conditions that you can derive for optimality in this optimization problem. But instead of this rigid condition of sort of, trying to get a sort of rigidity condition on how your m of t should be defined, there's also a relaxed optimization idea where you basically get a random ordinary differential equation for a relaxed profile where you dissipate a little bit and you do a gradient descent towards the minimum of this optimization problem. So there's lots of different ways, and this is actually in the community still a sort of matter of debate, so I cannot give you a final answer. What would be sort of the best way to track a stochastic wave? I find this reasonably appealing, this idea to say, I know my deterministic guy, let's assume the noise is something reasonable, at least small, so that you can sort of say there's some fluctuations around the deterministic profile and I'm optimizing my marker to track how far away am I from a certain deterministic translate. Okay, very good. So a little bit of brief history. This area has much more history than you would think it might have. So the early works start at least in the 1980s. There's a very old paper where the Nagumo equation is studied. So it says effect of a fluctuation on plane front propagation in bistable non-equilibrium systems from 1983. And there's lots of follow-up and works in physics in the 1980s. And there's a nice book by Jorge Garcia Oyalvo and Sancho where they summarized this work from the 1980s on spatial stochastic pattern formation. But then there is this whole zoo of people in the last sort of, I don't know, 25, 30 years who started to look at stochastic pattern formation with all sorts of different techniques. I only listed a few colleagues here. There are many, many more. And there's many sort of different techniques and equations that people studied. You know, people went to look at droplets. They looked at, you know, probabilistic techniques, and they looked at certain types of special coordinates that are moving. They looked at computational methods to track these stochastic waves. They looked at connections to integral equations like neural field equations and tried to track waves there. They looked at correction terms to wave speeds. People looked at, you know, the bistable Nagumo case a lot. And, you know, there's lots of work on stochastic traveling waves that might be a bit hidden in the literature. So let me point out there is plenty, but still the area is, well, evolving. Probably the number of papers is still on the order of like, you know, 50 or 60 in the area that you need to know. Okay. So here's the first result. I want to show a little bit of results so that you get a little bit of a flavor of a relatively simple result. So let's take the Nagumo equation. Remember, that was the cubic bistable guy. And let's suppose, I mean, you can put here on the top the normal Nagumo equation if you like. So think of this guy here as the normal Laplacian, but we also proved the result that allows for the discretization of the Laplacian, which in neuroscience that's sometimes necessary because there are these myline coating thingies that you have along an axon when you do the Nagumo and Fitzhugh-Nagumo equations, that you sometimes want a discretized version of the equations. But for understanding purposes, you could also say that this is the normal Laplacian. And then there's the bistable nonlinearity, and then there's a noise term that satisfies sufficient regularity and boundedness conditions and everything. And then you can show that everything is sort of well on the basic robust level. What does this theorem say with Carina Geldhauser? It says that if the noise is sufficiently small, and if the discretization is sufficiently fine, and if the initial condition of my stochastic equation is sufficiently close to a deterministic traveling wave, so that's what this assumption says, then the deterministic wave is robust, meaning that my stochastic solution stays close to my deterministic traveling wave solution, at least for a certain amount of time. So the probability that it deviates from that solution in a reasonable norm like L2 is actually small. So this is not surprising. This sort of says all the limits are fine. If you discretize, send H to 0, everything converges to the deterministic case. If the noise tends to 0, everything converges to the deterministic case, etc., etc. So this means that somehow you can at least say if you have a typical robust, stable, and deterministically stable Nagumo front. So this is for the Nagumo front, I should say. Yeah. So this is for the Nagumo front solution. Yeah. That Nagumo front solution is very reasonable, and you get it reproduced in the stochastic setting. Yeah, of course, we all know that there's no stable pulse solution for the one-dimensional scalar Nagumo equation, but we will get to that in a bit. But at least roughly this says under the influence of noise, this solution, which is the classical Nagumo front, is very robust. And many people have proven similar results to this. Yeah? So the proof idea is you somehow decompose the error. So you say, okay, there's an error from the discretization, there's an error from the noise, there's an error coming from the fact that you somehow start not quite directly at the wave, so you need some stability of the deterministic front. And if you sort of combine all this and crank the handle, you will actually show that indeed, via standard mild formulation solution and a little bit of Gronwall and bounding and Burkholder-Davis-Gandhi inequalities and so on, eventually you will see that everything is well behaved and all the errors can be made as small as you like with certain scaling laws and sigma and h and so on. And then the wave is indeed there. So the stochastic wave is there. And this means also to a certain extent, sort of these types of behavior that look like a normal wave are not an accident, they are normal. No? At least if the deterministic wave is stable. Okay, very good. But now you might wonder as a biologist, well, Nagumo, the one-dimensional bistable case, is not really a good model, because you know that there's no stable pulse solution, there are only stable front solution. So if you want stable pulse solutions, in particular neuroscience, you want that, you go to something like Fitzhugh-Nagumo or Hodgkin-Huxley or all sorts of various models that are of similar type. And there, for the deterministic case, there's a well-studied sort of families, many families of deterministic waves. There are two main families. One is a slow wave, where there's a slow deterministic speed. These are already spectrally unstable. This is well understood. And there are fast waves with an order 1 wave speed. These are spectrally and actually also non-linearly stable. And these are pulse solutions. So these fast waves are fast pulses that move and are just translated for this sort of modified or extended variant of the Nagumo equation. And the fast wave, it is linearly stable and spectrally stable, but there are some complications. It has an eigenvalue for the linearization. If you linearize, it is actually very close to zero, and close to zero in the sense of this sort of time scale separation parameter epsilon, which appears sort of here to show you, okay, U is fast and V is slow in this case, at least to a certain macroscopic extent. If you want to prove that in more detail, that's already hard. Okay, so now let's take this Fitzhugh-Nagumo SPDE and add the noise, and suppose we have additive noise with a sufficiently nice, specification of the noise, and you define a stochastic correction operator that's defined via relaxation. This is a little bit of a mouthful here. This equation is basically this random ordinary differential equation that tells you you're supposed to relax with your marker profile to the actual sort of, best possible or closest deterministic wave. And you're supposed to relax with this sort of with a certain rate R that you can specify as a parameter. Yeah. Then you actually can show that this sort of marker satisfies indeed the stochastic ordinary differential equation. There's again this relaxation parameter that basically just goes towards the sort of equilibrium that you are after, and there are fluctuations that are giving you basically the phase diffusion. And this second component here, let me explain what it actually means. It sort of means that this actual SODE is precisely along the direction of the translating symmetry of the pulse. So there's a translation symmetry in the problem that this pulse solution can be translated and you get another pulse solution. And if you linearize around the solution and you figure out, okay, what are the sort of eigen directions that are corresponding to the zero eigenvalue that is corresponding to the translating direction, you will find that that's precisely the derivative of the wave profile. And this is nothing else but saying I project my noise precisely into the space that's associated to the translating direction of my wave. So there is indeed a leading order description, at least in the leading order of the noise, of this marker that you can get via sort of a decomposition of your problem. And you can also find a stochastic partial differential equation that acts basically transverse or orthogonal in this Hilbert space. So you can actually find the fluctuations that are leading order. Again, the leading order fluctuations in the noise level satisfy a certain SPDE. And this SPDE, you can actually show that the sort of part that gives you enough damping to converge back to the wave is precisely, again, the linear operator that you're used to study stability of the deterministic wave. So roughly speaking, there's a balance here between deterministic linearized stability coming from an operator L and actually the stochastic fluctuations that get sort of squashed by this linear operator. And that gives you a way to study transverse fluctuations, transverse to the direction of translation. So that just got published in Annals of Applied Probability this year, but it's an older paper that is quite long, so it took a while to be reviewed. So, but now comes the fun part. Let's see how much time I have left for the fun part. Do I have something like 10 to 15 minutes? Is that about okay? Is that all right, or is that a no or yes?
Yes, you have plenty of time. 25 minutes even.
Okay, so then let me try 15 minutes and then you have time for questions. And so this is the fun part where actually we are going quite a bit beyond what has been known. So let me then go slowly on this. So this sort of stochastic traveling wave business is quite, already active for a while. And what we did in these sort of first two results were sort of refinements and improvements of certain types of results and, new techniques and trying to improve our understanding of these translating profiles when there's noise. But now there's actually this problem, what happens actually with more complex patterns? As you might know, in many sort of biological systems, just the wave profile itself might not be the only interesting pattern. For example, in cardiac dynamics, if you use Fitzhugh-Nagumo or Karma or the Fenton model or whatever, or the Barclay model, then you see that there is other interesting sort of shapes developing if the spatial dimension is not 1, but the spatial dimension is 2. So think of the normal sort of Fitzhugh-Nagumo equation, also maybe with additional bit of diffusion in the slow variable. Then you know that these types of models of 2-component, 2 spatial dimension reaction-diffusion equations with a bistability, they can produce sort of rotating or spiral type waves. You might know that these are related to cardiac arrhythmias, for example, but they're also sort of appearing in many other contexts, of course, in chemistry, for example. And here this sketch is from a sort of introductory PDE book for the deterministic case that I've written. So this is sort of a shameless advertisement for the book. So I guess I'm giving a talk in North America, so I can do a commercial break once in a while. It's okay. Football games, then they make commercial breaks all the time, so I can give a commercial break. So deterministically, these spiral and rotating waves are already very difficult. And stochastically, there was basically nothing. So there were numerical simulations, and there were sort of exploratory simulations, how these things behave, but there were no theorems. So we were sort of setting out to actually go beyond the numerical simulations and trying to prove something about the stochastic wave case. All right, so what are deterministic rotating waves for a PDE? Take your favorite 2-component, for example, system with 2 spatial dimensions. Then a rotating wave is a solution that has a certain profile again in X, but now this profile gets rotated in time by a certain type of rotation matrix. So basically you have a certain type of frequency, and that sort of profile gets rotated in time. And I assume that, this is one type of solution that I will see in my deterministic equation. So one important thing in rotating waves and spiral waves, there's actually much more symmetry now. Remember, for our sort of classical translating traveling waves, it was very important that we needed to figure out that the noise was actually acting along the translation direction, the symmetry direction of the wave. The wave itself is there, but also all the translates are there. So there's an entire family, but the symmetry group for a normal translating wave is the real numbers. It's the normal translation group. But actually for rotating waves, the symmetry group is actually a mixture out of rotation matrices, so SO2, and translation. So some translating vector B in R2. And if you look at this and you look at this sort of action of this group, then you see it's actually this special Euclidean group. And the special Euclidean group is basically all rotations and all translations. And this is, of course, a much bigger group. It's actually not 1-dimensional, but it's 3-dimensional. And there's classical theory, if you linearize around such an existing wave and you try to study the stability, you do not only get the classical 0 eigenvalue that you get for a normal sort of translating traveling wave, you actually get 3 eigenvalues, one that corresponds to the normal translation invariance, and 2 that are actually coming from the sort of neutral direction that comes from the rotation direction. And this means that now the linearization problem is much more difficult already in the deterministic setting. And we anticipate that in a stochastic setting that makes our life harder because there's now a higher dimensional subspace, a 3-dimensional subspace, where we have to figure out how the noise is acting along the directions that basically have neither decay nor growth. So it makes it harder. So there's a bit of background for rotating waves for PDEs that I will use. I will again assume that my nonlinearity in my equation, so this is my nonlinearity here, that's sufficiently regular, and there's an asymptotically constant rotating wave. So it's not a spiral, but it's asymptotically constant, meaning that if I go far enough out in the far field, then indeed this, this wave will actually decay to a constant. This will make my life easier. If it doesn't, we still don't know yet how to treat the stochastic case. Yeah? And even the deterministic case is hard. Yeah? I will assume that there's certain negative definiteness, meaning that there's essential spectrum is bounded away from a certain about a certain axis that is sort of vertical in the complex plane. So all the essential spectrum for linear stability analysis I can forget about. And the entire spectrum is actually basically very nice. It's actually contained in this set where all the stuff is very much to the left of this vertical axis. And it has these three eigenvalues that are neutral. And then Kuehn and Lawrence in 2008 proved a nice result that says if you perturb now a rotating wave under these assumptions outside of the center subspace, so if you are outside of the center space of these three directions that are neutral, then the perturbations actually decay in H2, for example. Sobolev space with basically two weak derivatives. And this basically says that a deterministic rotating wave under these assumptions is linearly spectrally stable. And you can even beef that up to nonlinear stability. So the next goal is we know we have a deterministically stable pattern in the same way we had a deterministically stable front or a deterministically stable pulse in the normal traveling wave setting. So how can we then analyze what happens with the stochastic case? How does it influence this deterministically stable rotating or spiral wave? Again, think of the case of cardiac arrhythmias. It would be very good to know how stable these are under noise. Okay, so this is the main result. The third result I want to present. You would take again your sort of semi-linear reaction-diffusion equation with a sufficiently nice noise and assume that G of u is suitably bounded and regular and has all sorts of regularity assumptions. Think of the nicest possible functions. And you assume that for no noise, you have PDE stability for a rotating wave. Then we define something that's, again, sort of a marker quantity, but that marker quantity is now more complicated. So instead of just having a scalar, remember the scalar marker was good because it was tracking the position along the symmetry group of the real axis. But now the symmetry group is not the real axis, but the symmetry group is actually SE2, the special Euclidean group. So it's rotations and translations. And the noise should act basically on these sort of three-dimensional phases. So we define a marker quantity that says we look at the normal rotating wave profile U star of X, and then we apply the group, but we apply the group at a certain sort of set of parameters of the group. And the set of parameters of the group, these are evolving. So basically, we are doing the same construction as before, but now we are parametrizing not by a scalar, but we are parametrizing by three parameters, or by three variables, I should say, by three variables that represent the three-dimensional directions of SE2, of the special Euclidean group. And since this is a Lie group, actually this effectively will give us a stochastic differential equation that's actually acting on a Lie group, or well, posed on a Lie group, I should say. So it's flowing on this Lie group, which is a group and a manifold. So it's a stochastic differential equation on a manifold. So we have to make sure that we take a chart from this manifold, and locally define this actual stochastic differential equation. And our goals where we want to derive a differential equation, and we want to utilize this deterministic decay, and we want to derive, so we want to derive something for the stuff that is perpendicular again. These W are all the components that are perpendicular effectively to the sort of phase diffusion directions. And we want to have a finite dimensional stochastic ordinary differential equation for the phase diffusion, how the noise is acting along these three neutral directions. And then we also wanted to get a large deviation type estimate to get an estimate how likely it is that this wave actually goes outside of a certain probabilistic neighborhood of the deterministic wave. Okay, these were the goals. And indeed, informal statement is we can do this. So I mean, I try to fit the technical statements on the slides, but the theorem alone is probably like 3 slides, and I don't think it helps very much if I present that here in this sort of setting when you're maybe more interested in the phenomenon and how you treat this basically and the biology. So I have to refer you to the statement in the paper, but roughly speaking, we can still derive a stochastic ordinary differential equation that's three-dimensional, that tells me how my sort of wave is spreading out due to the noise along the symmetry directions of the wave. And I can still derive a linearization equation that tells me how is the noise acting against the deterministic transverse stability of the rotating wave that was sort of used from this result of Kuehn and Lorentz. Okay. So the additional technical difficulties, we had really quite a lot of trouble adjusting these phase conditions. So we tried to define various types of ways of getting the phase right. One was more a dynamic variational phase where we adjusted the sort of phase condition, this relaxation condition of the optimization problem as we were moving in time. But the problem with that is we needed quite strict technical conditions to get that to work. And the second one is sort of an approximated variational phase that holds for a certain time, which is sort of more static. It doesn't adjust the optimization problem dynamically, but it gives us lighter conditions, but it only holds for sort of shorter timescales. We get certain new interesting operators out. So when you do the equations and you write them all down, you actually get certain non-commutative terms which come from the non-commutative part of SE2. So SE2 is not a commutative group, but it's non-commutative, and you get additional terms for that. Of course, the translation group that you have for a normal traveling wave is commutative, and we get new sort of, terms in the equations. And there's also correction terms that come from the geometry of SE2. I will not go to this into much detail, but there are correction terms that we get that weren't there before. And the third result that we wanted to get a large deviation estimate for a first exit time from a deterministic wave neighborhood. So think of your deterministic rotating wave. What's the probability that my stochastic waves leaves this deterministic neighborhood? And there I can sort of write down the theorem sort of on one slide, basically. So recall that the W is basically the deviation of my stochastic solution from my sort of phase diffused, translated, and rotated deterministic profile. So I take my deterministic profile, I translate and rotate and adjust that by driving it, basically this adjustment by a stochastic ordinary differential equation. And then the only stuff that's left over are the transverse directions that are outside of the symmetry directions, which should be damped out. And we can prove that there exist certain constants for sufficiently small noise that the probability that you go transversely outside of the neighborhood of the deterministic wave in the small noise regime is given by a large deviation type estimate that says the probability that you actually say, for example, an H2 bigger than a certain constant that is fixed is actually given by an exponential estimate. So it's exponentially small in the noise. That tells you, at least over a finite time scale. Of course, if the time scale becomes extremely long, then the probability increases, like for every large deviation estimate. And it tells you that if the noise is small, then indeed for a deterministically stable rotating wave, there's a low probability that you leave on a transverse direction the sort of neighborhood of your rotating wave. And the diffusion of the phase, again, is controlled by a three-dimensional SODE, and the mean escape time is also exponential. So, and currently we are thinking about and working on new dynamics for larger noises because many of these results are in the small noise regime. We are thinking about bifurcating rotating waves, for example, what happens with meanders. So when you have a sort of meandering of the center or the core of the rotating wave or the spiral and all sorts of other stuff. So how can we extend the mathematical theory for these spirals that appear in the heart and in many sort of chemistry problems further? And so then I should be at least roughly on time. And I thought I would aim for 45 minutes. And I think it's about 45 minutes, which is probably about right. And so for further information, please, all the papers are available for free. You can go to my website that tries to be easy to remember by its name. And thank you very much for your attention. It was really a pleasure to try to tell you a little bit about our work on waves. All right.
Great talk. Do we have any questions either online or in the audience? Check the chat. Okay, I'll start with a very basic question. So you've proven that these spiral waves are stable with respect to some additional noise. Do you find any conditions on their stability? Like diffusion coefficient have to be greater than the noise or anything like this? Like,
yeah, I mean, this sort of estimate already tells you in a way that, of course, the stability in the end will be linked to the fact that you need to control the sort of deterministic stability conditions relative to the sort of stochastic fluctuations. Of course, these are these constants that are basically appearing here, which I am hiding. Yeah, there are constants under which this is true. But roughly speaking, of course, the more deterministic stability you have, maybe you see this best in the case of the multiscale decomposition that we did for Fitzhugh-Nagumo. Maybe there it's more visible. Let me show this here. So on the bottom, you see this actually in some sense the best. So this is the leading order and everything, but okay. So this L basically gives you the conditions on how stable you are deterministically. And roughly this equation is an SPDE that tells you this sort of forcing term, the noise tries to sort of kick you away. And of course, depending on how big that is, relative to how deterministically stable you are, the higher and higher the probability becomes that you get kicked out of a certain neighborhood. So it's a typical result in stochastic analysis that sort of says, of course, all the other stuff like the diffusion coefficients, for example, of the Laplacian, they are hidden in this operator L. If you change those, of course, you're changing the relative magnitude of the deterministic pushing versus the sort of stochastic, deterministic sort of pulling together versus the stochastic pushing stuff apart. So yes, I mean, there are conditions that you could work out from the precise form of how these sort of things enter into the linear operator that is part of this transverse equation that tells you how the stochastic stability is controlled. So yeah, in principle, this is doable. Of course, the results are a little bit then, in the end, you have to choose a practical confidence level. Yeah, that's also a biological question in some sense. You can only show that there's a certain probability that you leave a certain neighborhood. Yeah. So here, for example, in this last result, you also see this very well. The large deviation estimate is, of course, relative to a certain choice of neighborhood. What practical sort of thing do I consider stable? How far should my H2 norm be away from my deterministic sort of wave? So how far should the perturbation grow until I say, well, this case is already, for me, biologically different. So it's like, 1 confidence interval, 2, 3, how many standard deviations do you want? There's a choice. And that choice comes from the application, actually. Yeah.
Very interesting. Thank you.
So any further questions? I don't know, maybe people are scared or don't want their question recorded, or
Yeah, maybe just a question. So here we have basically the 1D case and the 2D case. And what would be a general, what would be the result in 3D? Because sometimes the application we want to use are more in 3D. So it would be like, also a translation and rotations, and try to have, to describe the waves with respect to those translations and rotations.
Yeah, I mean, in 3D, it would probably then be a bigger symmetry group. I mean, if you would have a 3 spatial dimension case, then you would have SE3 probably, and SE3 is bigger. I don't know. I mean, so then that would just give you sort of a higher dimensional sort of phase diffusion. So there would be more directions along which the phase can diffuse. And I mean, you could probably extend that. And maybe the most interesting case that I know of in 3D would be scroll waves. These are these things that have been analyzed, I guess, also in biological problems in the 80s and 90s already. But there could be other sort of, certain types of patterns in 3D that rotate and oscillate. Yeah. But in principle, I would expect that these techniques are robust, that they generalize, except that, of course, this 3D, for example, result would then become, I don't know, a 60, 80, 10D result. It would have more dimensions. So these equations become then, of course, more and more complicated to analyze, because you, of course, want to take your parameters, stick them into the sort of phase diffusion equation, so seeing how your noise acts along your symmetry group. And then you want to sort of utilize that to gain an understanding of the influence of your parameters on the sort of phase diffusion of your wave. And the higher dimensional this becomes, the harder, of course, it becomes, right? So the harder it becomes to sort of think about how do I analyze, an 8D stochastic ordinary differential equation. Yeah? So it's probably possible to write it down mathematically, but the practical use, of course, then becomes much harder. Yeah. Oh. All right. Well, are there further questions, or I don't know? Okay, then I guess
not so much. Yeah. Thank you once again for the great talk.
Okay, sure. You're welcome. And if you have further questions and stuff, of course, you're free to email me at any time.
Right. Thank you also for staying up so late to give this talk.
That's okay. I mean, it's not like 3 in the morning. It's still somewhat manageable, right?
Yeah. Okay. Well, I wish you good night and goodbye.
Yeah, goodbye. Nice thanks for the invitation, and maybe see you sometime live soon. Bye bye.
That'd be great. Bye.
Thank you.